have got a problematic soil, let's say soft clay that you see here, you cannot build your structure on top of that to withstand the earthquake load. We have different strategies, and that's the topic of the two researchers that we have here at UTS. One of them is looking at shallow foundation or raft foundation. Means we have a very large foundation, we put it there and then we monitor the results and see how it behaves. The other one, which is more challenging one, is pushing the piles into the soil. If you have got a soft soil, there is no way that you can construct your building on top of that soft soil. So what you need to do is that you need to push piles depending on the depth of the material that you have. Let's say if we are in some Asian countries, you may pile, or you may have a bedrock closer to the surface so the pile can grow and reach the surface. So all these things basically they have to consider, so we have considered different types of foundations. So what we have got here, we have got 3 tons of soil, so that's what is there. The weight of the container, which is 300 kilograms, and the weight of the structure is roughly 110 kilograms. These things basically scale the structure. We have got the geometric scaling of 1/30, means we are simulating 15-story building with 45 meters high. So that's the scale down of that structure, and as you can see, it has got 15 levels. The natural frequency has been scaled the factor of 1/5, and that's what is important. We're going to scale the earthquake using the same factor, so we will have the same result on this structure. We have scaled the stiffness, cross-sectional area, and length of the piles basically into the material that is suitable. Later on, we can have a closer look to the foundation there. We have got piles and all those things they have been scaled. The main parameter of the pile that has been scaled is the stiffness of the pile. So it means the stiffness should be scaled in a way that the foundation will behave similar to the real case. It means the deformation of the foundation will be scaled similar to the other scaling factors that we have. The soil that we are modeling here has a shear wave velocity of 45 meters per second. This shear wave velocity of 45 per second by itself is very soft soil. Soft soil, we are classifying soft soil as the shear wave velocity below 200 or 150 meters per second. The actual material that we have got is very soft soil. But when you scale it up, the actual soil that you have inside and here has a shear wave velocity around 200 meters per second. Still, it is kind of soft soil, but a bit higher range of soft soil. So that's what we can test here. The actual material is a real soil, has got the combination of bentonite, 20%, 60% kaolinite, and 20% fly ash class C. We have got several instrumentations here that we are monitoring the performance of the structure. We have got 14 strain gauges which are embedded inside the soil and on the pile. So we are monitoring the movement of the pile and strain on the pile, so we can calculate the bending moments generated in the pile. And of course we can calculate the deformation of the pile. We have got accelerometers that will measure the acceleration transfer from the base to the top. So we have installed this one in 3 or 4 different locations in the depths of the structure, in depths of the soil, and some of them right below the foundation. We believe that the acceleration right below the foundation will be different than the acceleration we have got close to the sides, and that is hopefully proved in this project. We have got 6 extra abilities outside there that is monitoring the deformation of this structure. What is unique about this structure is that it's simulating 15-story building without any simplification, without major simplification, I should say. The last test that has been done in this field is a, let's say you may say a bit a smaller case, but 1 degree of freedom. Means rather than putting the actual structure there, they put a beam and 1 mass there, hoping that will give the same result. In this way, we can calculate the shear generated between 2 stories using a parameter called inter-story drift, which is giving us how much 1 story moves against the other story. And it is one of the new parameters, or one of the parameters in the new design views, which is performance-based design earthquake engineering. So hopefully the results that we collect from here after analyzing will show that we are going to simulate several earthquakes today, and hopefully we will see all those earthquakes today. We have got selected 4 standard earthquakes for this test. That's Northridge, happened in USA in 1994 with a peak ground acceleration of 0.84 G, called gravity, and the magnitude of 6.7. It lasted 30 seconds, that side. So here we are scaling it down with a factor of 5, so it's going to be something around 6 seconds. So that's the earthquake we're going to apply. We have got Kobe earthquake with a maximum acceleration of 0.83 and magnitude of 6.8. El Centro earthquake and Hashimo earthquake, basically these ones will be applied as well, which are far field earthquakes. The first two, which are Northridge and Kobe earthquakes, are near field earthquakes. So as you can see, the magnitude or peak ground acceleration is higher than the other 2 earthquakes. So basically that's the test we are going to do, and hopefully that will be interesting for you guys. That's very unique test. We believe that no one has done it in the world, not in Australia. In Australia, basically we have the biggest shake table, I believe. So definitely that's very unique in Australia, but this setup is very unique in the world. You may ask this question, that why we are doing this sort of research here at UTS. Maybe Australia by itself doesn't have much earthquake. The last earthquake happened was maybe 20 years ago in Newcastle without any deaths and maybe 20, 30 injuries. But what do you see? We believe that Australia is the leader in Asia Pacific in engineering, and we have a lot of international or national companies that serve overseas, and we have to deliver good design. It's not something we say we don't have the expertise and we cannot. So it's very easy. You may see that the companies working here, several of you, I can see that it works or they are already working. You get assignments going overseas. So if you go get assignment in Japan, in Europe, in Indonesia, these are the countries that basically Australia has a very close relationship with and work very closely. So these are very basically important points to consider for development of the companies and relationship between countries. So the reason is very obvious, basically. There. So I don't want to make it very long. After that, I think we are happy to answer the questions. Here I need to appreciate the work of several people that have been involved. Perhaps we are working in a group. We have got Professor Vijan Samali from the structure and stream that is helping us with this. We have got 2 PhD students which are working on this project, Hamid Reza, Abadar Waifar, and Asnan Sadeghi. So these 2 guys basically worked 6 months to design this and assemble this one. The test that you see here takes, let's say, 1 minute. For earthquake, we apply everything like, let's say, 5 minutes maximum. We have worked 6 months just to make this setup. So you see that how tedious this work has been. Filling this container, that's not very easy. That's not very usual that you put 3 tons of material in such a big container and then put the structure, make sure that it's absolutely flat. So these are a lot of details that need to be considered in the numerical model. And of course experimental work. So I think the very
as already mentioned, we're testing the 15-story model here. It's got end-bearing tiles in it. The first test work you're going to conduct is a Chinaha, 100% intensity. It's been scaled in the frequency domain. The time at the moment is 11:23, and it's the 4th of May 2012. Acquisition ready? Okay, the test is going to start now. Test complete. Okay, we'll do the second test. Obviously it's a 15-storey building with end-bearing piles. This time we're going to be subjecting it to El Centro at 100% intensity. This is also scaled in the frequency domain. The time is 11:24 on the 4th of May 2012. Data acquisition ready. Table starting now. Test complete. Okay, the third test, the same model was on the table. This time we're going to be subjecting it to Kobe, also at 100% intensity and scaled in the frequency domain. Table of acquisition ready. Test starting now. Now moving on to the last test. It's the 15-storey model with end-bearing piles. This time it's going to be Northern Ridge at 100% intensity, scaled in the frequency domain. The time is 11:26 on the 4th of May 2012. Data acquisition ready. Test starting now. Test complete.
Oh, flip it. The scale to go. They have scale time, for example, for 30 seconds. Yeah.
Other rounds that we do. So what you see here, this foundation, this slab of concrete is not sitting on top of the soil. If you put it right on top of the soil, this system is called pile raft foundation. This one at the moment, it has got a gap, it means we are only mobilizing the forces and the stresses inside the piles. Means the only basically system of foundation that we have got here, which is holding this structure against the earthquake, are those piles inside the ground. So the strain gauges, which are these ones, connected, basically going through the soil and connected to basically this pile, to the depth, several of the piles. I think we have got about 4 or 5 of these piles instrumented. Go there and record the strength and moments there. These ones that you see here, we have more, but several of them at the moment we haven't installed it for the simplicity. Is that those equipment that they measure the displacement. If you have got the displacement, if you differentiate it with time twice, that will give you the acceleration. We have got these blue lines connected right on top that they measure the acceleration of the structure on basically those points that they are connected, 2 on top and 2 on other levels. We have got several other of the blue lines as you see there. They are gone into the soil, they measure the acceleration in 3 dimensions. So these ones, let's say they are 2D, those ones that they have now 1D, let's say these ones they are 3D. Means any movement in any direction they can capture and see what sort of airscope you apply. Obviously the airscope you apply here is in one direction. You haven't just, if you rotate this one, you can do it in 2D as well. So is there anything Vijan and Aslan and Hamid?
Comments, if you don't mind, for further clarity, a couple of thank yous before we go to students. Let me do the thank yous first. I think a special thanks should go to Peter. Peter has been working extremely hard, staying back 8, 9 o'clock, many nights. And of course the 2 students. I think Hamid and Aslan have been working extremely hard, especially Hamid. I could not reach his arm the other day, has gone so much thicker because of carrying so much weight lately in the last 6 months. So guys, well done. And of course to Rami and his team who has made this possible in the lab. So thank you to all of them. And also to Dr. Lee, my colleague, who with Peter has spent several days. So much work has happened behind the scenes. Like simply tuning the table. I can explain 30 seconds about what it means. This table is like a piano. If it's not tuned, it's no good. The table is about 6 tons, but when your controller doesn't know that it is 10 tons, so when you put the signal in, the output signal is not the same as what you put in. And of course, we don't want to put something, we don't want to put Mexico earthquake and the output is Kobe. It has to be the same. So what you have to do, you have to tune the table. And it took about 2-3 days of solid work to do the tuning right. You might also wonder, what about this rubbery type? Why didn't we just put one solid boundary? These boundaries have to have special properties. We call them quiet boundaries. When the earthquake wave goes, they have to be absorbed at the boundaries and not to reflect back, to interfere. Because in the real field, and then we had to go and find the company and go and with Aslan and finally found the divisible rubber and they had to cut it, test. So much work has gone to just find the right materials and the manufacture of the container, which at the end of the day, you look at it, it's a black and silver container. But we don't know how much work has gone behind the scene. One final thing is, now that Reza has given me the opportunity, a few times we have mentioned this question of scaling earthquake. To some of you, the earthquakes were too short and not exciting enough. Because a real earthquake takes 30-40 seconds. So let me just explain why is the case. The real building that we estimated through numerical analysis that Aslan and Hamid have done has a frequency which is much lower, about 2 seconds per 1 cycle. This model, because it's scaled down, is much faster. It's about 5 times faster. So when the model is 5 times faster than the actual building, in order to have the same dynamic conditions, you have to make your earthquake 5 times faster. So an earthquake that takes 30 seconds, what do? In the time scale, we just shift it by 5 times, so it becomes 5 times faster. Therefore, the duration from 30 seconds drops to 6 seconds. And that is why what you saw, it finished so quickly. Otherwise, the earthquakes are not that quick. But the intensity was very much the same. With the impact on the structure, we didn't scale the intensity, we scaled the time. Just one final comment. You notice the first 2 earthquakes, the structure responded fairly gently to it. Hachinohe and El Centro. Those 2 earthquakes, we normally refer to them as far-field earthquakes. Earthquakes that happen somewhere and then it takes some time to get to the site. The last 2 earthquakes, Kobe and Northridge, you saw a big jerk. And that was responsible for almost most of the devastations and failures. And this one huge peak is typical of the earthquakes. We call them near-field earthquakes. Earthquakes at the source of earthquake is very close to the site. So if you saw a big difference in response, that's what actually happened. So I thought with that, we have almost covered everything. If there is any question. Oh yes, I think I'd be happy to do a gentle science sweep.
Actually, this container, as said earlier, model free field exactly has enough boundaries, stance, and we have got viscous boundaries in here, as you can see. When wave is spread into the soil, it doesn't come back to the structure because we have got very viscous boundaries. And actually, the main influence of the soil underneath is just reducing the shear wave velocity and internal force, but at the same time, it increases the lateral formation and interstory drifts. So what happens then? When interstory drifts increases, the performance level of the building that we may consider is life safe may change from life safe to near collapse or even total collapse. Apart from the force reduces, but when lateral deflection increases, you may change the performance level to very dangerous area. So at the end of the day, when you put it on soft soil, it direction and technically inter-story drifts. So yeah, that's it.
We don't apply science to it, but we apply for earthquakes again. Just repeat the earthquakes one more time. So, and that's it. So,
back and forth. Anytime any of those frequencies of the table I was going through matches the frequency of the building, you have the condition we call it resonance. So you get a sudden shake. And our colleagues and the students are worried that if that happens, they may not have a building left to test for 10 and 5 stories. So to respect their wishes, especially 6 months of effort, you don't want to ruin it by looking exciting. So sorry for, but that is a very
Longer, maybe.
Paper cheetah hat, 100% intensity, scale in the frequency domain. Are you going to record the data or you're not? No? Okay. Well, the table is going to start
Why not?
now.
You gotta put a cup. You gotta put a cup of glass on the top of it.
Test complete.
Why don't you? That's it.
far-field airplanes. Of course, far-field airplanes have another problem, and they can excite very tall buildings. The reason is that the airplane has all kinds of frequencies in it. Soil can filter out the lower frequencies, and sometimes when they arrive, they only have, the high frequencies filtered out. Only low frequencies get to the buildings, and tall buildings have low frequencies. So you can see an earthquake happens 500 kilometers away. All the lower buildings are okay, only the structures are 40, 50 stories start to shake.
Test starting now. Test complete. The third earthquake, it's Kobe at 100% intensity, scale in the frequency domain. Test starting now. Test complete. It's North Ridge, 100% intensity, scale in the frequency domain. Table starting now. Test complete.
Before you go, just talking about earthquakes. The second earthquake that you witnessed, El Centro, is probably the most widely earthquake in the world in terms of design. A lot of codes use this earthquake as a design earthquake, it has very interesting features. The magnitude is not very high, but it has all kinds of frequencies and the energy is very much there. So it's a good earthquake for really exciting all kinds of buildings. The third and fourth earthquakes are also interesting. Coincidentally, both of them happened on 17th of January, 1 year apart. 17th January 1994 in Northridge and 17th of January 1995 in Kobe. What's important about the last two is that it happened in places that have designed the building for earthquakes. It did not happen in like BAM or some other places that they don't do it. And yet the nature told engineers, I know more than you do. And we had very bad damage, 5,400 people killed in Kobe, and freeways collapsing and so forth. Same, a lot of freeways failing in Northridge. So after 94-95, the earthquake engineering entered a new era. We thought we were mature, we went back to infancy in trying to build it again. So I can say the modern structural engineering in the field of scientific engineering is only 17 years old. Because 94 and 95 earthquakes in those two countries told us we don't know anything